So continuing with SBlock element, next question is, this is our lecture 5, SBlock. Question is, give structures of monomer, dimer and polymer of BeCl2. So monomer of BeCl2, it is like this. Then we have dimer, then we have polymer, so these are the structures of monomer, dimer and polymer of beryllium chloride. Then we have question number 2, define diagonal relationship give its cause and establish it between lithium and magnesium. So diagonal relationship, it is defined as the resemblance in the property of a particular element of a second period, particular group of the second period, and the next an element of next group of the third period, or the elements of second and third period which are placed diagonally, they show resemblance in their properties. This relationship is called as diagonal relationship. Now what is the cause of diagonal relationship? It is the resemblance in the properties of the elements of second of a particular group of second period and next group of third period, or elements of second and third group which are placed diagonally so similarities in property this is known as diagonal relationship. So lithium, beryllium, boron, carbon, nitrogen, oxygen, sodium, magnesium, aluminium. So these elements, this is the element of second period. This is of third period. This belongs to the second group. It belongs to the third. This belongs to the first group, and this belongs to the second group. So the resemblance in the properties of the element of the first and second group which are placed diagonally, so similarity in their property, this is called as diagonal relationship. Now we will discuss the diagonal relationship between lithium and beryllium. Now what is the cause of diagonal relationship? The cause of diagonal relationship is when we move top to bottom, the atomic size increases and left to right atomic size decreases. But when we move diagonally, then atomic size does not change much, ionization energy does not change much, electropositive character does not change much, they almost remain same. That's why the properties of these elements they get repeated. Now we will be considering the diagonal relationship between lithium and magnesium. Both of these metals they are quite hard. First, both of them are quite hard. Both have high melting and boiling point. Then chlorides of both metals have some covalent character. It is due to their small sizes. Both evolve hydrogen on reaction with water. Give hydrogen on reaction with water. This is forced resemblance. Both form nitrites on reaction with nitrogen. Mg3n 2Li3n. Then we have nitrates of these elements produce ammonia on reaction with water. On heating with oxygen they produce oxides. Li2O, MgO, carbonates of both decompose on heating. MgCO3 decomposes to give you MgO plus CO2. Then nitrates, carbonates of these compounds, they also decompose on heating. Nitrates on decomposition, they produce NO2 gas. So this is diagonal relationship between lithium and magnesium. So diagonal relationship, it is the resemblance in the property of the elements of particular group of the second period and next group of the third period, or the elements of second and third period which are placed diagonally, they show resemblance in property. This is called as diagonal relationship. And cause of diagonal relationship is when we move diagonally, the periodic properties like atomic size, ionization energy, electropositivity and ionization energy, these properties they do not change much, they remain almost constant. That's why the diagonal relationship is seen between the elements of second and third period. Then we have next question, question number 2. Give preparation and uses of quicklime CaO How it can be prepared? CaCO3 on heating decomposes to give you CaO plus CO2. This is called as quicklime. This reaction takes place at 1273 Kelvin. The reaction is actually reversible. To prevent the reversibility, the CO2 produced is allowed to escape from the system so that the reaction is not reverted at all. Then we have properties of quicklime. It is white crystalline solid. It is soluble in water. CaO combines with water to give you calcium hydroxide. This is called as milk of calcium or lime water. It is used as a laboratory reagent as well as it is used for whitewashing. Its melting point is 2870 Kelvin, which is very high. Then CaO reacts with carbon dioxide to produce CaCO3. It produces CaCO3. It reacts with ammonium chloride to produce ammonia. It is used in the preparation of cement and as a flux in the metallurgy, and it is also used in the preparation of number of compound glasses, cement, and then we take the next compound, give preparation and uses of lime water. Lime water is prepared from CaO. By mixing it with water, we get CaOH twice. This is our lime water, calcium hydroxide. When carbon dioxide gas is passed through it, it is white liquid used in whitewashing. And medicines. CO2 turns it milky. CaOH twice combines with CO2, giving CaCO3, which produces milkiness in the solution. If excess of CO2 is passed, then milkiness will disappear. No milkiness is seen. It is again heated, again milkiness will be there. Then we have, it is a white fluffy solid, CaOH twice, CaCO3. Next, CaCO3 is calcium carbonate, preparation of calcium carbonate. Also, it can be prepared by passing carbon dioxide through lime water. Or combining quicklime with carbon dioxide. It is a white fluffy powder. Upon heating, it decomposes to give you quicklime and carbon dioxide. It is used in the building material in metallurgical operations. Then we have next compound. What are gypsum and Epsom salts? Gypsum is CaSO4 to water. This is called as gypsum salts. And MgSO4 having 7 water is called as Epsom salt. They can be prepared by treating metals like calcium and magnesium with sulfuric acid, or their oxides with sulfuric acid, or sometimes their hydroxides with sulfuric acid. They will give gypsum and Epsom salts. Now gypsum salt, it is sparingly soluble in water. On heating at 398 Kelvin, it will lose 1.5 molecule of water and will give you plaster of Paris. CaSO4 having 2 water molecules, when heated at 390 Kelvin, it loses 1.5 water molecule and will give you CaSO4 plus half H2O. This is plaster of Paris. It can also be written like this: CaSO4, 2 unit having 1 water. This is called as gypsum. Then Epsom salt, they are used in agriculture. They are the magnesium salts. They can be prepared. Epsom salt, it can be prepared from Mg, it can be prepared from MgO, it can be prepared from MgSO3. All of them, they are treated with sulfuric acid. They all give MgSO4. In case of this, you will be getting water. In upper case, you get MgSO4 plus hydrogen. In the last case, you get MgSO4 plus carbon dioxide plus water. So this is Epsom salt. On crystallization, it takes up 7 water molecule and will form Epsom salt. It is used in the agriculture purposes and is used in the preparation of organic compounds. Then we have the next compound, uses of P.O.P, the plaster of Paris. It can be used in the plastering of bones to repair the broken bones. It is used in the preparation of chalk, in the preparation of statues, in the preparation of models. So all these compounds, they are prepared from gypsum. Gypsum salt is also used in the agriculture to increase the agricultural yield. Then we have the next important question of this unit, that is cement. So our next question is, define cement, give its composition, and preparation. Cement, it is finely divided mixture or finely powdered mixture of number of silicates, aluminates and ferrates of calcium and aluminium. The composition of cement, it contains 50 to 60%. CaO is 50 to 60%. This is called as calcareous material. Then we have SiO2, that is around about 25 to 30% SiO2. This is called as argillaceous material. So these are the two major components of the cement. We have Al2O3 5 to 10%. It helps to increase the binding capacity of the cement. MgO 2 to 3%. We have Fe2O3 1 to 2% Fe2O3 is there. SO3 1 to 2%. Along with that we have sodium peroxide, sodium monoxide 1%, K2O 1%. So these are the material which are used in the preparation of the cement. Now the raw material used to supply CaO, they are called as calcareous material. Clay provides SiO2, Al2O3. Gypsum supplies calcium. The other material added directly to the cement preparing slurry. The raw material, that is limestone and clay, they are mixed in the ratio of 3:1. This will be 3 parts, the remaining are in the ratio of 1 part. So they are mixed in the ratio of 3:1 by mass and are then made into paste or slurry with water. Slight water, they are changed into paste. This slurry is introduced from the top of the cement kiln, and from the lower side of the cement kiln the hot gases they are passed, which heat up the cement kiln round about up to 1800 Kelvin. Now when the slurry moves down, the kiln is like this. From top of this the materials are added, and from bottom the hot air, hot gases, they are passed. The kiln has 3 parts, the upper part, middle part and lower part. In upper part temperature is about 1000 to 1800 Kelvin. In lower middle part it is 1000 to 800 Kelvin. In the lower part it is up to 800 Kelvin. So whenever these materials they come down in the upper part of the furnace, whole of the moisture goes off. Then in the middle part of the furnace where temperature is 800 to 1000 Kelvin, CaCO3 decomposes to give you CaO plus CO2. In the lower part CaO combines with aluminium to give calcium aluminate. It combines with silica, dicalcium silicate. This is dicalcium aluminate. It combines with Fe2O3 to give you dicalcium ferrate. So these substances are formed, they start forming from the middle of the furnace, and when they reach at the bottom of the furnace, this combination is complete, and at the end we will be getting cement clinker from the bottom. So we will be getting lumps of the cement. They are taken out from this cement kiln. They are crushed into powder state and are mixed with the required color and 1 to 2% gypsum, and then they are packed in the bags and are sent to the market. This is the preparation of the cement. So cement, it contains dicalcium silicate, tricalcium silicate, dicalcium aluminate, tetracalcium aluminoferrate. It also had tetracalcium. 4CaO combines with Al2O3 plus Fe2O3 also. You will get 4CaO dot Al2O3 dot Fe2O3. This is tetracalcium aluminoferrate. They are used in the preparation of the buildings or large cement structures. They are being built from it. And then we have this cement clinker. They are mixed with 2% powdered gypsum, and the required color is mixed in them, and then they are packed into bags and are sent to the market for sale. Setting up of the cement: when cement is mixed with small amount of sand and water, and sand reduces its time of setting and gives uniform setting. and it is mixed with water and gravel and some other material. Then after within 8 hours it settles into a hard mass, and this is used highly nowadays in the construction of the building. Now cement is highly used nowadays in the construction purposes, construction of roads, construction of building. So this is regarding cement. Now what is the biological importance of calcium and magnesium? Biological importance of calcium and magnesium. So calcium, that is required for the healthy formation of bones and teeth. In the adult body requires around about 25 milligram of calcium and 200 milligram 25 milligram of magnesium and 200 milligram of calcium a adult body needs. Calcium ions, they act as biocatalyst in number of biochemical reaction. Magnesium is used as antacid in the form of MgOS twice. Magnesium, you know, it is also the component of the chlorophyll, which is used for photosynthesis by the plants. Why alkali metals not found freely in the nature? It is due to high reactivity of alkali metal. They are not freely found in the nature, but they are found as oxides, halides or sulfides. And now why sodium metal is kept in kerosene oil? Sodium metal, due to high reactivity, it can combine with the oxygen and nitrogen of the atmosphere. Therefore, to prevent its activity against nitrogen and oxygen, it is kept in kerosene oil. Kerosene oil cuts the supply of oxygen and nitrogen and prevents its compound formation with nitrogen and oxygen. Then why lithium fluoride is almost insoluble in water, but lithium chloride is soluble in water? Lithium fluoride is insoluble in water because of its high lattice energy, but lithium chloride is having less lattice energy, so it is soluble in the water. Why LiCl is a covalent compound, but NaCl is ionic compound? Why LiCl a covalent compound, but NaCl is ionic compound? LiCl is a covalent compound. It is due to small size of lithium and its high polarizing power. It polarizes the electrons of chloride ion and brings a cloud of the electronic cloud of the electrons of chloride ion on itself and acquires covalency between Li and Cl bond. But the polarizing power of sodium ion is less, therefore it cannot bring the cloud of chloride ion above it and does not introduce covalency in NaCl bond. That's why LiCl is a covalent compound, but NaCl remains ionic compound. Then we have the question, why MgOS twice? Is weak base. Then NaOH. Answer, it is due to small size of magnesium. It is capable of forming stronger bond with oxygen. So OH ionization is less probable in MgOH twice, but it is more probable in case of the NaOH due to large size of sodium. Therefore, NaOH can easily produce OH ion in the aqueous medium as compared to MgOH twice. That's why we say that magnesium hydroxide will be a weaker base as compared to the sodium hydroxide. So this is regarding the S-block elements. Then we have the comment upon characteristics of properties of nitrates of alkaline earth metals. Nitrates are normally hydrated in the crystalline state. Upon heating these nitrates of alkaline earth metals, they get decomposed to produce metal oxide, NO2 gas and O2 gas. Then we have comment upon characteristic of sulfates of second group elements. The sulfates of alkaline earth metals are quite stable and do not decompose on heating. but at very high temperature they decompose into metal oxide, sulfur dioxide and oxygen gas. Generally they are stable. Then comment upon stability of carbonates of alkaline earth metal. The metal carbonates, they are insoluble in water of the group 2 element. They decompose on heating to produce metal oxides and carbon dioxide. The thermal heat stability is increased from top to bottom. If we go from beryllium carbonate to radium carbonate, thermal stability go on increasing. It is due to increase in lattice energy when we move top to bottom. So this is all about S block elements.